Welcome everyone. This is a stream where we do geometric algebra programming. Here we're making an animation program. We're making it using lots of geometric algebra. A lot of it has just been talking so far, and today is going to be no exception. Not going to see much code. You're going to see reasons why we use geometric algebra. All right. I've been a game programmer for, I guess, a bit more than 10 years. A lot of people have been game programming for much longer than that. Geometric algebra has always been there in kind of in the background of 3D game engines. So it was used in Tomb Raider. A lot of people it wasn't used in Quake. They used Euler angles for all of the rotations there, and in some sense didn't use geometric algebra. But yeah, the potential of geometric algebra it can't be understated. All right, like it will make the game industry very significantly better if a lot of people adopt it. It's kind of technical to describe because the dot product and the cross product, which is what geometric algebra is trying to replace, those things take, kind of an undergraduate course to describe. Yeah, and so there's a lot of talking, but you only hear about the motivation exactly once in a while. What are the reasons that you want to use geometric algebra? And I'm going to give you there's a huge number of reasons to use geometric algebra. There are as many reasons as there are geometric problems that you might want to solve, which is a lot in a video game engine. But I'm going to try and summarize kind of the main reasons. So here we go. Number one, because you don't want your animations to look terrible, all right? Animation quality. This is why Crytek uses a little bit of geometric algebra. And by that I mean they use dual quaternions, which are a pretty advanced mathematical structure to be using. Disney also use dual quaternions. Unity doesn't. That's because, Unity is a bit of a dinosaur now. The Unreal Engine, as I understand it, does not as well. And that is to its detriment. There are animations that you cannot import into the Unreal Engine because it's not compatible with dual quaternion animation, whereas in the CryEngine you can import those animations. But anyway, yeah. Well, I'll say a little bit about animation quality, but to say the other things. So number two, properly understanding quaternions and homogeneous coordinates. Now, and I want to point out that every single game engine uses these. Unity, Unreal, CryEngine, Frostbite. If you've got it, show me a game engine that doesn't have quaternions and homogeneous coordinates, and I'll be kind of surprised. I guess it would be something that an undergraduate would make as their first game engine. That's forgivable. But I want to say a bit about the philosophy at this point. Software engineering is not in a very good place, and it's getting kind of worse. We're in a sad, but interesting transitional period, and it's not easy to know what the future is. By which I mean, there's a lot of people who are now oldish, who understand the fundamentals of software engineering better than any of the young people. Now, maybe that's always true. Maybe that's always true of any engineering field. Like the people who learned to program in the 1960s will have understood assembly language a lot better than people who learned to program in the late 80s. I would guess. But the situation that we have in the games industry is that, well, the games industry is an interesting, exceptional industry for software engineering as a whole because we care more about performance than other parts of software engineering. We do write assembly language sometimes. We do count cycles. We make a heck of a lot of the use of the GPU. We don't just put everything on the CPU, and we don't and we're not always using assembly language, but we're using languages that compile closer to assembly than other languages. So we are, in a sense, better off than other software engineering fields. But games industry and also computer graphics, I want to say, we still have the same problem of like, well, people like John Carmack, Jonathan Blow, Sean Barrett, Mike Abrash. These people are now, well, they're not super old, but there's a generation below them, right? And well, I'm part of that generation, I guess, and maybe some of you guys watching this are as well. And they're not going to be around forever. That's a rather morbid thing to say, but they're going to retire and this kind of thing. And the people underneath them, the next generation needs to be able to understand what they're doing. And that's so the stereotype that we have now is that you have like stack exchange programs and this kind of thing. Okay, I want to get to the other point, but it's really important culturally for people to understand what's really going on underneath a game engine. And it may sound a bit weird for me to say that, given that I'm proposing that you learn kind of a new thing, which is projective geometric algebra, which most game engines, in some sense, are not based on. But the idea of projective geometric algebra is that all of the stuff that Unity is built on, all of these math functions, become wildly simpler if you use projective geometric algebra. And the things that these game engines already have in their quaternions and homogeneous coordinates, which are a version of projective geometric algebra, I would say. Oh, do you know what? And homogeneous planes. That one is less of a bugbear than these other two, quaternions and homogeneous coordinates. But all three of them are in all game engines. Homogeneous planes, people don't... They feel like they have an intuitive understanding of them. There again, if you look into the function that, for example, you've got two planes and it takes the intersection of those two planes, it gives you the line of intersection of those two planes. Probably most game engines have that function. And if you look at it, it'll be, again, scary math, just like the quaternion and homogeneous coordinate functions. How are we doing in the chat, by the way? Are there a bunch more people? I don't know. Okay, we've got a few more people. Freeze John Carmack, or clone him or something. How about that? Yeah. Some... John Carmack is interesting because, he says on Twitter from time to time that though he has a reputation for being very, very, very good at math, he's like, oh, I'm not that good at math. I just do well-applied high school math. It's interesting that he says that. Homogeneous coordinates are definitely not high school math, unless you went to an incredible school. So... I can see maybe he doesn't concern himself with quaternions that much. He concerns himself with optimizing the code that's already been written, which is a very respectable thing. But yeah, so he's not. Yeah, I would doubt that John Carmack was writing the inverse kinematics stuff. There again, I feel like I saw John Carmack say specifically that he copy-pasted a load of the quaternions code that he used in his, space rockets into the code that he was using for his virtual reality headset, calibration or whatever it was. Fun story there of a very hardcore programmer that we should all aspire to be more like. So... John Carmack's got to be interacting with quaternions. And certainly his game engines do, but whatever. Okay. All game engines interact with quaternions. No getting around them. And number 3. Well, performance. And debuggability. extendability, by which I mean um, extendability is you've written some code that does a thing and it implements a feature in your game. Great, you're happy with that. 3 months later, it doesn't have any bugs, but you want to do something with it. You want to, okay, let's say that it's the code that causes flowers to go from side to side. And now you've decided that you don't just want them to go from side to side, you want them to blow in a radial fashion whenever whenever an explosion happens or something like that. There's probably code that you're going to keep, some code that you're going to take away, but in any case, you're going to be interacting with that code that you already have. And if you do things the crappy way, vector algebra, as opposed to geometric algebra, then it's going to be a pain. Whereas if you don't, composability, somebody's saying here. Yeah, I suppose composability is another word for this. Yeah, you want that experience to not be. You know that you're going to be having to do a lot of stuff like that. There's no shipped game that's any good where most of the code was written once, where all of the code was written once and then it was fine. It was just there forever. You don't need to extend it again. Oh, and it didn't have any bugs in it, by the way. You want your code to be. You want it to be readable. You want it to be understandable. You want it to be. There to be as little as possible. I could phrase this one as you want there to be a small amount of code. Other things being equal, which sometimes they are, not always, but other things being equal, you do want to write less code rather than more code. By which I mean, if you can implement the same functionality in a way that involves writing that causes less code to do that, then you should use the less code version. Once in a while, okay, sometimes I'll take a single line of code and I'll break it up into 2 lines of code. That's the only example, that's the only counterexample to that I know, really. And I'm sitting here saying that geometric algebra makes your code more understandable. Obviously, there's a caveat to that, which is that you're learning some new maths here. You're learning new maths, and because your thing is using new maths, that means that not everybody is going to understand it. So I guess in some sense your code is less understandable. But it's, here I get to one of the main reasons that people don't use geometric algebra. It's because new math means that your thing is slightly less compatible with a lot of the code that's out there. And certainly if you're, the stereotype of like a crappy Stack Exchange programmer who's just like, oh, I want as many people to write my code for me. If you're a parasite, right, then yeah, you want to use Python and NumPy and Pandas or whatever the big hot, and React. You want other people to write your code for you. And that's, yes, that's, other things being equal, quite a nice thing to have. However, it makes it so that if you're an undergraduate, if you've only been programming for a year or two, if you only program once in a while and you only need to do like a tiny little thing, you really only need to do a tiny little thing, fine. You don't need to learn that much stuff, and it is just generally speaking a good idea for your code and your knowledge to be compatible with what everybody else does. But not everybody can be that way, and if you want to consider yourself, hardcore, if you want to consider yourself self-reliant and, the person that people can turn to when they're confused by something that's really important and everybody else is confused, they need somebody to talk to. ChatGPT isn't giving them the answer because ChatGPT has been trained on just all of the text and all of the, Stack Exchange as a whole is not an expert on quaternions in general. It's it's an average of computer graphics programmers. And if there's some misconceptions out there, if there's some ways that people are using quaternions that are not the ideal way to use quaternions, then ChatGPT is going to reproduce that, at least so far as I can tell. Maybe AI is going to make it so that, humans can sit back and not do anything. If we really are in that situation, then fine. Everything that I just said is false. But, like, well, AI seems to be mostly an average of it's mostly an average of engineering. It's not necessarily an expert on every single little thing. That's what I've found so far. And it seems likely to me that it'll be that way forever. But forever? It'll be that way for a very long time, because that's what neural networks are in some sense doing. They're regressing to the mean. Anyway, blah, 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 blah. We got a question. I work a lot on Figma-style applications that need rotation, scaling, and translation in 2D. Does geometric algebra have any advantages in composability there? Yes. So it depends on whether you're scaling it. So, okay, rotate. I suppose. Yeah, 2D. You're saying. Do you know what? Well, yes. So 2D projective geometric algebra is useful for translation and rotation. It only comes into its own in 3D. In 2D, you can get away with a lot, but okay. So for example, yeah. If you want to rotate, if you're interested in, okay, I've got a rotation around somewhere that isn't the origin, and I've got another rotation around somewhere that isn't the origin again, and you want to compose this rotation and then that rotation, then geometric algebra gives you a way of doing that. Your only alternatives in that, if you do the naive implementation where rotation translation is like, rotations are always around the origin, and then if you want to rotate somewhere around that isn't around the origin, you have a function in your code that does a rotation and then does a translation. That'll get confusing very fast. So yeah, you do want to use 2D projective geometric algebra in your case. I am going to be talking about 3D projective algebra, geometric algebra, 3D. I'm going to be talking about 3D mostly. But yes, you specifically want to look into 2D projective geometric algebra, which, I mean, just to say it briefly, it looks like this, E1, E2, E0, versus this, E1, E2, E3, E0. This does 3D, this does 2D. All right, but we're not going to be talking about this so much. That's your question answered. Happy to take more, but in general, the purpose of this is going to be for 3D programmers, so graphics and video games. I guess also, well, if you do CAD software or you do robotics, for example, you've got to program something that's happening in 3D. Well, actually, projective geometric algebra was originally developed with robotics in mind. Yeah, but it's turned out to be. I would say it is the foundation of what video game engines should be based on. Okay. Performance, debugging, and extendability. So to say a little bit about performance, people have the stereotype of game programmers that we are all obsessed with performance. And yes, we all care very deeply about performance for reasons that geometric algebra is not mainly about performance, and there are some cases where, there are a lot of cases where geometric algebra is the same level of performance as vector algebra. There are some cases where the naive version of geometric algebra will be a little bit slower than this, because, for example, if you apply a dual quaternion to a vertex, that is a bit slower, than applying a 4x4 matrix to that vertex, which is not to the credit of dual quaternions. It must be admitted that is a problem with them. However, given that you care about animation quality, you are going to be using dual quaternions at some point, unless you don't care about animation quality. The lowest quality version of dual quaternions is still faster than 4x4 matrix version. The 4x4 matrix approach, yes, it is. Well, nobody uses that nowadays. That would be something that you'd use on the original PlayStation. So yes, your vertex shader implementing dual quaternion animation is slower than the very fastest thing you could do, but it'll have terrible quality. Blah blah blah. It's a trade-off, but you do want performance. Geometric algebra is not exactly about performance. In many cases, it will be more performant because there's a huge quantity of code. Like, inverse kinematics code is going to be way faster in geometric algebra. And lots of other examples. Again, arguably dual quaternions. But yes, there's cases where, for example, if you want to apply a dual quaternion to a vertex, the fastest way to do that is to convert the dual quaternion into a 4x4 matrix and then apply that to the vertex. I think there's a faster way of doing it, but it uses some, floating point fiddling that you wouldn't really consider geometric algebra. Anyway, but it helps performance, and it helps performance significantly because, again, your code is more understandable. Well, okay, one thing that it does, it makes your code more inlineable. So, instead of calling the function that does, get me the quaternion that does rotation from this vector to this vector, you can inline that function, which makes it so that you can maybe realize, oh, I actually didn't really need to call this function. I can actually combine it with this other function that's in my function body, and that'll make something that's simpler and faster. Whereas you might not see that if you don't understand geometric algebra well enough to inline that function. Okay. All right, so going back to animation quality, let me show you what I mean when I say that. So no, this one. Okay, so here is a video which will help you understand what I mean. So what you're seeing here is linear skinning, as it says in the top right. So, as you know, in animation, we have these bones on the inside, right? That's what you're being shown in here. So you've got a bone, you've got two bones, and you're rotating one with respect to the other, and that's causing a change to your mesh. That's what you want. This is good, all right? Well, this is what everybody uses, and this is not something that I'm proposing we should change. This works really well with geometric algebra. The surface of the mesh is trying to follow what the bones are doing, and in doing that, it is getting pulled really, really tight in the center there, which, if this material was supposed to be made out of, a balloon, you might want that. You really might want that. Realistically, most video games animations are not about having balloons pull up tightly. So, let's look at the second half of the video, where... Oh, sorry. This is dual quaternion skinning. Alright? And you've actually got the bones doing exactly the same thing. You've got the bones doing the same thing that they were doing back here, right? But the surface is doing something different with dual quaternion skinning. And that is because dual quaternions blend differently to matrices. In fact, ordinary quaternions blend differently to matrices. For that reason, that's part of why quaternions were originally introduced into game development. But they didn't quite go all the way. They said, oh, here's this beautiful this very useful mathematical formalism from 2 centuries ago, almost 2 centuries ago, which helps us out. Let's use it. And we can take this, quaternions do rotation. We will take our rotation, which we calculate with quaternions, we will put it into a 4x4 matrix, and our 4x4 matrix will let us do rotation and movement as well, and then we're going to blend those. That's what they said. that doesn't work. That doesn't. You've got to commit to it completely. You've got to use dual quaternions. A dual quaternion lets you do rotation and translation. Um, and translation on its own is, you might say, a super easy thing to do. You might say, oh, if I want to if I've got a point and I want to move the point over here, that's super easy, right? All I've got to do is add something to the coordinates. Well, yeah, that kind of works with vertices. If you're talking about vertices, sure, that works. If you're talking about, for example, planes, you want to move a plane, turns out that doesn't work. You can't just do that with planes. You generally can't just do that with lines. You've got to use different kinds of matrix with it. Generally, that's how people do it. Blah, blah, blah. But the point is that this is a more realistic thing for human flesh to be doing as opposed to this. Human flesh does not do that. The leading candidate here, by the way, is like shoulders. Shoulders were a horrible thing to animate. And, there's a lot of animators out there who use Blender and they use Houdini and they use 3D Studio Max or whatever, and they get this behavior by default, all right? They get the crappy 4x4 matrix version, and they deal with that, and when I say they deal with that, they put in all sorts of little corrections. They spend a long time doing this thing called weight painting. They sometimes add an extra little bone here that you don't really have in your actual body. They sweat and they cry, and their blood and their sweat and their tears gets smooshed together into the final animation that people see. And the person who programmed Houdini and 3D Studio Max and Unity looks at that and they're like, oh yeah, that's fine. Because they didn't see the blood, sweat, and the tears that went into this. They're too lazy to do this, to give people this version. But that's not you. You're watching this stream. You want to give people the proper version. You care about quality. You don't care that it's going to cause like 1 or 2 extra cycles to do the dual quaternion version, and you certainly don't care that it's going to require you to do some extra maths, because you're not scared of the maths. You're going to learn some new maths. The new maths is going to let you improve quality, and it's going to let you do those other things. So you're willing, right? And the maths is even going to make things simpler from your point of view. You're going to look back on the cross product and you're going to say, what a bunch of scrubs that would want to cling to this stupid, untype-safe, performance-reducing, complexity-increasing, extendability, debuggability decreasing thing. Yeah, that's going to be you. Because the cross product is stupid and ugly, and it really doesn't save you that much time. It really should be put into a rocket and blasted into the center of the sun. I guess this one is maybe going a little bit far. I guess this is comparing dual quaternion with log matrix. Basically, log matrix means I'm gonna temporarily turn my matrices into dual assume that they're dual quaternions, do a bunch of math, and then and that's why it's slow. But yeah, so linear blending is super fast. That's again what you might do on the PlayStation. But again, look at this thing. Like, yeah, that's nasty. Oh, and by the way, if you introduce an extra bone here, well, that might push your array of bones that you're sending to the GPU from being 32 bones to being 33 bones, and now the performance is slightly lower. Do we have any questions at this stage? Let's have a look. Okay, do I have any good hints for interpreting the numeric values of 3D PGA? I most certainly do have a lot of hints. I'm looking for things similar to reading the columns of transformation matrices. Yeah, so okay. I gave a presentation at the Game Developer Conference a while ago. That'll help you out. TLDR, the way of reading off a PGA element is, first of all, if it's got one index, then it's a plane. If it's got two indices, then it's a line. If it's got three indices, then it's a point. If it's a scalar, well, it's the identity transformation. And if it's got four indices, then it's most likely to be almost certain to be a part of a dual quaternion that turns a rotation into a rotation translation. That's the TLDR. Slightly longer. You want to get used to seeing these things as what they are, which is compositions of planar reflections. Okay, they are planar reflections. Even if it's just a plane, well, a plane is a single planar reflection. If you've got E1, well, that's the x-axis plane. That is the planar reflection in this plane, right? E2 is the planar reflection in this plane, right? If you've got E1 plus E2, addition, this is really helpful for interpreting numeric values. Addition is always mixing. So if you have E1 plus E2, so you've got which you'd store as, it's an array. It's always an array of floats at the end of the day. And your array of floats has a 1 for the E1 coefficient and a 1 for the E2 coefficient. So it's 1E1 plus 1E2, as in 1 multiplied by E1 plus 1 multiplied by E2. E1 plus E2 equals this plane, all right, which is directly in between these two planes, because addition is always mixing. All right, and this works for quaternions. If you take two quaternions, this is it. Okay, it links directly to what I was just saying. If you take two quaternions and this quaternion is this rotation and the other quaternion is that rotation, then adding them together, by which I mean the x part of this quaternion plus the x part of this quaternion, the y part of this quaternion plus the y part of this quaternion, the z part of this quaternion plus the z part of this quaternion, the w part of this quaternion plus the w part of this quaternion, that will always be a quaternion that is in some sense like the rotation that's kind of like this one and kind of like that one, all right? Yeah, and that kind of and it's always guaranteed to be just a rotation, and that is why a quaternion is better than a matrix, either a 3x3 rotation matrix or a 4x4 matrix. If you add together the components of two 3x3 matrices, then even if they were both rotation matrices to begin with, you will probably get a rotation and shear matrix. Whereas shearing, here's the other fun thing that I wanted to show you folks. This is the one video game that I know of where somebody actually purposefully used shearing. Shearing is usually a bug. Again, this is the only exception I know of. This car is shearing whenever it turns, and it's kind of cute. But most video games don't make use of this particular animation technique. Yeah, and they're doing that by literally taking two. Well, I'm not positive that they're doing it this way, but I'm very, very confident that they're doing that by taking the matrix representing the car's current transformation and like linearly interpolating it to another matrix, which is usually a thing that causes an animation bug, but in this case is causing something that they wanted, which is the shearing, also known as skewing. But in the case of geometric algebra elements, if you add a reflection to a reflection in this plane to a reflection in this plane, you get a reflection in this plane, which is the plane that happens to be directly in between them. If you've got a rotation and translation and another rotation and translation, add them together, you will get a rotation and translation that is, let's say halfway between these two in some sense. If it's like this, and by the way, it's intuitive because, if it's a 90-degree rotation around this axis added to 10-degree rotation around this axis, that'll give you a a rotation again around this axis that is in between 90 degrees and 10 degrees. Okay, and that's the TLDR for my advice about interpreting numeric values. I don't know how long I was talking for there, but it's, well, it works better than matrices in some sense. That's animation quality, I guess. Maybe you're not an animation programmer, though. Maybe you're a gameplay programmer. Fine. Yeah, it's obviously, ideally, you would be able to implement it, in theory at least. You would understand the engine that you're working with well enough that you could implement the whole thing yourself. Properly understanding quaternions, homogeneous coordinates, and homogeneous planes. Alright, quaternions, famously, there's like, if your company has 100 people in it, there's like the one person at the company who understands quaternions. You can go and ask that person. I had the horrible experience this week of seeing a fake understand. Like somebody understood somebody said that they understood quaternions, and they gave an explanation of them that didn't work. Like they tried to. Well, I won't try to repeat their explanation, but like, okay, apparently there's fake explanations of quaternions out there, and if those are common, then ChatGPT probably knows about them. So but you want to actually understand them, and you will actually understand quaternions because quaternions are a part of geometric algebra. So I might as well do I say understand quaternions? What by this I mean, there's a couple of functions that'll work with quaternions. Maybe you've only got a small number, but like, what will they be? Like maybe you'll have you've got this vector and you've got that vector, and you've got a function that gives you the quaternion that takes you from here to here, where the axis is like that. So that's one function you have, vector to vector. Another one that you might have is applying a quaternion to a vector. So let's say that you had like this vector, and you wanted to apply this quaternion to this vector to get that vector, right? Right, so it's like this, That's the effect that not a particularly good drawing, but it's going like this, right? It's applying that. If we call that V, then that might be V. Well, it's V with the quaternion Q applied to it. All right. If you open up the code, you take whatever engine you're working with, Unity, Unreal, 3JS, whatever else. You open up the function that does that thing to that vector. It'll be a scary looking function, It'll be and you want, but it's not a particularly long function. It's not particularly worth me showing it to you. It's like 10 to 20 lines of code, but it's all like multiplies and adds. So it's like some kind of linear thing that it's doing. Well, I don't know. Yeah, it's a linear thing that it's doing, it's not very interpretable. But if you understand GA, then you will be able to understand it. Like I do give an explanation of this in the lecture that I just linked to. It's the part involving Harry Potter and Dumbledore. To give a summarized version of it, what you do is you have a function that you have a formula that looks like this. So Q V and then Q inverse. All right. Where what am I doing here? Well, in the most proper sense, what I'm doing here is that I'm saying Q multiplied by V using the geometric product. It's the geometric product of Q and V, followed by. No, I don't want that in red. In black. Let's have it in dark blue. No, let's have it in white. Followed by, have that in brackets. Followed by multiplication using the geometric product by the inverse of Q. that might seem a little bit like another thing. I guess the thing that turns people off geometric algebra is that you have a relatively more simple formula for matrix multiplication. Like, let's say I have a matrix M and I've got V. And that formula is all that you need to do to apply M to V. If M was a rotation that represented the same rotation as Q, then yeah, that's done. That's done the same thing as this formula. And let me complete it, by the way. So that equals V. So my original, oh dear, I mislabeled those up here. So let's call this one V prime. You got V, you start out with V, ugh, that doesn't look very good. So V0 and V1, right? You're starting out with V0, you're rotating it and you're getting V1. And that gives you V1, and to make it a little bit easier to look at, I guess we're adopting the convention that vectors are drawn in black. Let's erase some of that. V1, V0 in there. Doesn't look very good, but you get the idea. We're applying Q to V0, and we're applying M to V0, and that gets you V1, assuming that M is the rotation matrix that was gotten from Q. You will also have a function in your video game math library that takes a quaternion and gives you the matrix that does the same thing as that quaternion. Useful thing to have sometimes. So, okay, this one looks simpler than this one. But this one is wildly more complicated for the reason that I described earlier, which is that if you're talking about planes and lines, maybe even circles, then this is, oh god, this won't work to start with, or rather, you will need to have another matrix. Let's have it. It's another matrix, M alpha and M beta. Right? These are two different matrices representing the same quaternion, because this one is for the situation where so this one is for M being to apply to points, and the technical term for this is the contravariant. Yeah, the contravariant matrix. And then this matrix you need if you want to apply to planes. Q apply to planes. Yeah. That's the covariant matrix, and that's the contravariant matrix, both of which begin with C, so I couldn't write MC. And gets even worse if you're thinking about lines, or at least certain kinds of line. There you need something called the adjoint thing, I think, or the adjunct. And, both of those exist, a bazillion different kinds of matrix to represent a single rotation. And so, this is a poisoned chalice, all right? It's a poisoned chalice. It looks simple to begin with, but this, my friends, this works whether you're interested in a point, a plane, a line, a circle, a conformal transformation, another quaternion. It's the same formula. So this is the code that you will find if you open up the function within whatever game engine that you're using that does axis angle to quaternion. All right, that's a very important function. You use it around. I've not got numbers, but both of these are used fairly commonly. Yeah, both used fairly commonly. And this is the code that does it. This code, as I've said before, it kind of makes some intuitive sense. Like it should make sense to you that you have to use theta, And it should make sense to you that inside of the quaternion is like the axis of the quaternion, which is like x, y, z, basically going into there with very little modification. And it shouldn't surprise you that you've got a cosine and a sine involved in here, because cosine and sine are related to rotations. You learned that part in school. The thing that you could be forgiven for being very surprised by is, why on earth do we have this factor of 1/2 that we apply to our theta, and then we take the cosine or the sine of that. And to be honest with you, people often ask, and it's a very good question, why didn't geometric algebra get adopted? Why didn't it get adopted instantly? Well, do you know what? I think that this factor of 1/2 is the main culprit. And when I say culprit, I want to be clear that I love this factor of 1/2. I want to marry this factor of 1/2 and have, half human and half quarter babies. No, half babies. It's a really beautiful thing, but it's related to something that's really weird and exotic and unfamiliar, that takes a bit of thinking to wrap your head around, which is the double cover. Quaternions have the ability to represent rotations that are clockwise or counterclockwise. This quaternion, a lot of you have seen this 10,000 times before, but this quaternion and this quaternion, all right, that get the pen to the same place. The pen ends up this way, versus like that. Look, the pen's ended up the same way. Those are two different quaternions, even though they result seemingly in the same rotation. One of them's clockwise and the other one's counterclockwise. But yeah, that thing there, it's really beautiful actually, and you frequently do want to have a distinction between clockwise and counterclockwise. But the guy who invented / popularized the cross product, who was Oliver Heaviside, essentially, very important guy, very intelligent guy. He hated that the quaternions had this factor of 1/2 in them, and he was like, well, I guess I could sort of forget about the double cover thing, forget about this, forget about clockwise versus counterclockwise, because if you got a, I'm gonna sort of think that like a rotation like this. Well, if you want to do a rotation that way, you could just do a rotation that way, but, from the other side. So it's like the axis is sort of different, because you could rotate around the vector pointing this way as opposed to the vector pointing this way. That might give you the same thing. And the cross product, so it's not as sensitive as the quaternions as in terms of distinguishing those two different situations. Well, I've gotten very far into the maths now, I realise. This is sort of more far than I wanted to go, but this is my thinking. That's why, not that anybody asked, why the cross product won in the first place. All right, I wanted to talk about homogeneous coordinates and homogeneous planes as well. So homogeneous coordinates. I'll say briefly the geometric algebra version of homogeneous coordinates, because it's beautiful. Homogeneous coordinates, you've got points that are sort of vectors, and you've got another kind of vector, you might say, which is a point at infinity. Let me draw the proper picture of this. Again, it's a picture I've drawn many times before, but it's an important picture to be drawing. So here we've got like a perspective picture. All right, you've got maybe like your railroad track, and you've got some like trees, and there's another tree over here that's a bit smaller, and you've got the sun in the sky. All right, And a ordinary point, a vertex, you might say, is like a point that's like, let's say it's a point that's like an apple in the tree, the position of an apple in a tree. But there's another kind of point, which is a point that's a bit like a star in the sky. This kind of point, you call it an ideal point, and it's a point at infinity, and you represent it with something that looks like this. So you have like x, y, z, 0, and then this point here is x, y, z, 1 down there. All right. If you work in computer graphics, this comes out of nowhere. You're just told to swallow it because that's the thing that you need to apply your 4x4 matrix to. Why do you need a 4x4 matrix to apply? You need the 4x4 matrix because you're doing perspective transformations. Why does it need to be a 4x4 matrix? Why does it need to be applied to seemingly four-dimensional vectors? Just don't worry about it, man. It's just the way it is. Yeah, but if you work in geometric algebra, you get to say this. So, yeah, and this is a good as time as any to say one of my favorite things about GA. You can ask the question, suppose I've got a plane. I haven't drawn any planes here. So, how about this? So, suppose you've got a plane like this, and suppose you've got a line like this. All right. And those, you might ask the question, what's the point where these two meet? Point? What color are points? Points, let's have them in green. All right. It's a point. That's where the purple line meets the grey plane. If you were doing things the ordinary way, in an ordinary video game engine, you have your plane, you have your line, you have a function that gives you this point, and that function, you can ask the question, hey, what if I want to get the intersection of this plane with a parallel line, right? It's a line that's completely parallel to this plane. You might have some if statement. You would have the function return false. You might even throw an exception if you were really... I don't want to think about that. But if you do geometric algebra, then what you find is that this plane meets this line in a point that's an ordinary kind of point, a red point like an apple in a tree, and then this plane meets this line in a point that's, I'm going to say, infinitely far in this direction, in some sense. And projective geometric algebra shows you how that's related to the fact that you can have a rotoreflection or a transflection. So a reflection like this. So I reflect this hand to get this hand, and I rotate after that. So now my hands are related to one another by a rotoreflection. This is a rotoreflection. And then this is a transflection. So I reflect this hand to get this hand, and then I translate. And geometric algebra, those are very natural. Those are extremely natural visual things that you can teach yourself about with your hands while you're on the bus. And this shit where you just get, it comes out of nowhere, the W coordinate comes out of nowhere. Yeah, I'm not going to go into too much more detail about that, but if you watch my GDC lectures, I do go into detail about that, and geometric algebra offers you insight into why it is this way, why the coordinates need a fourth thing in there. Okay. That's homogeneous coordinates. Homogeneous planes, well, yes, those are in there as well. Similar sorts of things apply. Okay. Performance, debugging, and extendability. I guess I've gone on a little bit long now, and I guess I've already talked a bit about performance, but I've already given you an example of the debuggability and extendability thing. So again, thinking about the function where you've got the grey plane and the purple line, or purple lines, and you've got the point where you want the point where the line meets the plane. If you do that in your game engine, here's what happens. You think to yourself, oh, hey, I need the intersection of a line and a plane because, this line is my laser sight and this plane is like my wall. And I need to get the intersection of those so that I can get the point where I put a bullet hole. Fine. And then at some point, possibly by, some error that you have to chase down, you're like, oh, it's like it's given me not a number or something like that, or it's divided by 0 or something like that. And then you're like, oh yeah, because the laser sight can be parallel to the plane. Silly me. Okay, fine. If you were well acquainted with projective geometric algebra, you would always have known that was an option. And if you're a seasoned game developer, maybe you also wouldn't make that mistake. You'd instantly say, oh, as soon as I'm intersecting a laser sight with a wall, I'm in the situation where I've got to think about where they're parallel, and deal with that somehow. If you haven't written the code that does this intersection thing, well, the code to do that, if you look it up on Stack Exchange, it's like 25 lines of code. And then there's some, let's say, subjectivity about how you handle the parallel situation. If you do projective geometric algebra, this is one line of code. It's, let's see. So the plane is P, and the purple is L. It's P. Well, I'll write it out like code. You'd usually say it as P wedge L. Well, do you know what? It's that. That's what it is mathematically. And then if you write that's called the wedge product there. And if you write out, and if you want to write it out as code, then you just do, all right, come on, wedge brackets P, comma L. I've done the L in the plane's color, and I've done the P in the line's color. Apologies, folks, but you get the picture. You get the symbols, huh? And then the thing is that same function will also give you the intersection of two planes. That same function yet again, I don't use it this way, but if you want to use it this way, you can use it to get you a number which will be related to it'll give you if you take the wedge product of two lines. So let's say if I was interested in L1 and L2, I was interested in the relationship that these two lines have to each other, which is something like this. If I take the wedge product of those two lines, I get a thing that tells me the distance between those two lines, which is nice. Why does it tell me the distance between those two lines? Again, I go into it in my lecture. I'm not going to go into it here, but this is a very versatile function and a very mathematically interesting function that you can understand with some practice. That's nice. That's the opposite end of the spectrum of being a Stack Exchange shitty programmer who copy-pasted somebody else's code, didn't even think about the situation where they would be parallel. It throws an exception at runtime when the situation never came up during the time when the game developer was testing it, but then it does on some poor, user's machine, and then they don't know what's going on and the game crashes because it's divided by 0. Okay, I'm not aware of a particular situation where that has happened. It's the kind of thing that happens in this day and age, though. You don't want to be shitty Stack Exchange programmer. You want to be like John Carmack or Sean Barrett or Jonathan Blow, or John Selig or Eric Lengel or Stephen DeKennick, gotta say it. Yeah, you want to be a person who can be relied on by their colleagues to know the answers, and could, if you were on a desert island, make your own game engine. Yeah, that's who you want to be. Don't want to be crappy Stack Exchange programmer, unless ChatGPT takes over everything, which you're kind of screwed anyway. All right. And that's what I mean by debuggability and extendability, and even performance as well, because the function that the function that does the intersection of a line and a plane, it might be doing some calculations that you don't need to do. For example, let's say you're in the situation where you knew. I find it difficult to think of an example off the top of my head, but you were wanting to find their intersection because you wanted to know the distance between this point. This point and something else. You want to know the distance between this point and some other thing up here. Well, if you inline it, you might notice that some of this algebra actually simplifies, and I don't have to use the whole wedge product. I could just use this part of it or something. That's nice. That's a nice situation to be in for performance reasons and other reasons. And that's. I hope I've given some idea of why we care about this. Really. Okay. Final reason. It's beautiful. This is not the main reason that you do this, because you're probably an engineer. If you're a mathematician, you like thinking about maths all day, then this will be your main motivation. But if you're an engineer and maybe you don't even like maths, you only care about maths to the extent that it helps you solve the problems that you have, which are problems that you care about because you want to create something that your user wants. Projective geometric algebra is still a good call for you, because, and for all of the reasons that I've just described, but it seems very unlikely that a person could look at this stuff and come away with the impression that the cross-product way of doing things was the more beautiful one. It is not more beautiful. It's very ugly. It is very it's a hack. It's kind of the archetypical example of a hack because, again, it's sort of not type safe. This is maybe worth mentioning. Just say about the cross product. So, an analog of what the cross product does is, let's say you've got a plane and you've got another plane, right? Right, and you want to get the line of intersection of the two planes. Lines were in purple, so nothing to be done. Right, you want to get the line of intersection of the two planes. That's something which, absent projective geometric algebra, you would use the cross product for, probably. Or you use the cross product at some point. If we assume for the sake of argument that those are two planes that are through the origin, there's the origin, then you can set, that's a situation that the vector algebra, fan would say, I just imagine like the normal vector to this plane, and I imagine the normal vector to this plane. I take their cross product, right? And I get this vector here. Well, I guess I've got it. Yeah, I'll just draw it like that. And that's the vector that's pointing along my line, right? That's something you can use the cross product for, and fine. But I want you to notice that the cross product has taken two vectors that you related to planes and given you another vector that you relate to lines. Which means that if you want to apply a matrix to some of these things, and that is involved in the problem that you're trying to solve, you will get strange results. And unless you're on top of the different matrix representations, which very few people are, so Eric Lengel is, for example, then yeah, you'll probably screw yourself up, and you won't know why. One thing that I used to do was, like, if my quaternion stuff didn't work for some reason, I'd try to find a way of switching from using this way of making my quaternions to using this way of making my quaternions. God, that's horrible. Get rid of that. Yeah. So, and that was a silly programming thing to be doing. That's the kind of thing that you would do if you didn't know why you were getting weird bugs. In projective geometric algebra, you do understand why you're getting your bugs. You're the elite. Yeah, you're the boss. And that's most of what that's what I meant when I say that the cross product is not type safe. Projective geometric algebra is, because you have a separate you have a set in your code. You have separate things for plane, line, point. All right. And that's what I wanted to say. I'm going to check if there are any questions. Okay. Philip Trudeau has his mind blown. That's what I want to see. All right. It feels like the anti-cross product stance of GA has parallels to the anti-determinant stance in some parts of LA. Yes, that is true. LA so is linear algebra, and so this is something that I'll rapidly. I'll say what I know about this. Let me say what is meant by this by BYP64. There's an interesting essay called "Down with Determinants," which is written by one of the world's leading experts on linear algebra, which is a guy called Sheldon Axler. I think he wrote it. And Sheldon Axler also wrote a very influential text on linear algebra. So much of, matrices, much of AI is based on Sheldon Axler stuff. And indeed, the determinant. First of all, I've not read the essay. I can make some guesses about what it says. Like the determinant does give you, if you got some matrix and you take its determinant, which is a scalar value that you get with a pretty elaborate but ultimately, well, at least tractable series of multiplications and additions of the elements of the matrix. That's the determinant. It's a scalar value. Yeah, Axler is linear algebra done right. Thanks. That number is supposed to give you some insight into what the matrix does. So I think a big example is that if the certainly, rotations all have determinant 1. Yeah. I guess rotoreflection. No. I'm not gonna try and say more than that. But I do know at least that part is right. There's some other conditions as well, I think. Yeah. So the determinant is giving you some information, but the sad thing is that it's sort of not. It's a kind of information that's pretty thin. It's pretty thin. It's not that informative. And the thing that Stephen says is that the trace and the determinant are the main two things that give you insight into a matrix that's used in conventional linear algebra. If you do geometric algebra, you have, to be clear, you certainly do have ways of extracting the same information. It's complicated to say what exactly the translation is from this world to that world, but you can still get that same information. A really interesting thing to me is that John Selig, who invented projective geometric algebra, more or less. Well, yeah, he did. He once said in an email to me that geometric algebra he views as primarily a way of avoiding determinants, right? So he's very much in the avoiding determinants, avoiding taking determinants. So he's very much in the Axler camp there. Oh, you missed the first half of the stream, but you don't know what the wedge product is in the first place. Do you know what? Thanks for bringing that up. I thought it would be a good idea to say this. So just a little cheat sheet here, all right? If I've got two things, A and B, where I'm talking very abstractly here. So A and B could be points, lines, planes, rotations, translations, screw motions, rotoreflections, whatever. They could be anything. A, B, and you can take the product of anything with anything. A, B is called the geometric product. We've got A comma B, A, B, and it is transform. Composition. So the geometric product is acting a lot like matrix multiplication. So it's kind of like a generalization of the quaternion product, all right? Well, kind of like it is a generalization of the quaternion product. That's how it was originally discovered. The geometric product is transform composition. The wedge product, wedge, and this one basically does intersection. There's a few other places that it comes up. And I want to, and a thing that's interesting, useful, is that it turns out that the wedge product is a part of the geometric product. There's an intuitive reason for that, which is that if you've got two planar reflections and you do a reflection in this plane followed by a reflection in this plane, you will get the line where the two planes meet each other. Sorry. Reflection in this plane followed by reflection in this plane will give you a rotation, all right? Reflection followed by another reflection where the planes are at an angle will always give you a rotation, and the rotation will be around the line that is the line where the two planes meet each other. And so that's why the wedge product, the intersection operation, is found as part of the transform composition operation. Got the inner product, which basically it's like the dot product. So it does a few things. One of the main things that you use it for is getting angles. To be honest with you, I'll write out this. So theta. This is a hand wavy product that I'm drawing here, but theta equals a cos a dot b. There's some things that I'm skirting over there, but that's basically true. The arccosine of the inner product of a and b will be theta. So basically it's acting like the dot product, and in fact the dot product is a thing that was discovered by taking the quaternion product and separating out this inner product part, and here we have restored it to its natural home alongside the wedge product, which is a bit like the cross product but better. Within the geometric product, because the inner product is a part of the geometric product as well. And I guess I could mention the commutator product as well. That one's a bit more advanced, but let me just say this last one, A dot B. How about this? So A, B, inverse, which, I don't know, division. You might say it's geometric division, which sounds weird, but the point is, it's more or less from B to A. So, or rather, it's from where B takes you to where A takes you, which is useful if you're thinking about a quaternion and another quaternion. And you want to know how is it useful? It's quite useful. If you want to get from a point to another point, you more or less use this. I guess I could have. I'll also have the A dot B times by B inverse projection. Well, is that the name for it? It is the projection formula. And it does projection. So if you've got a point and you want to, if A is a point and B is a plane, then that'll project your point onto your plane. And if A is a line and B is a plane, then it'll project the line onto the plane. It's great. All right. And I guess the last one that I want to have here is A, B. I have at least already talked about this. This is the sandwich. And this is application of a transform to a thing, which could be another transform. In fact, it always is another transform in some sense, but points, lines, and planes are always transforms. In addition to being in addition to being shapes, they are also transforms. So yeah. And are there any other questions? Nothing else? Super useful table. Thanks for that. Glad to hear it. Very, very glad to hear it. Yeah, and I think we might end with that because that is quite a nice, useful table. Okay, I want to be clear that the inner product, I have cheated a bit. I do not cheat in my lecture. You can go and watch that, and it will give you the true stuff. All right, and it sounds like there are no other questions, so I'm going to stop it there. So long, everyone.